So what are the basic concepts related with the interfacing of input and the output device? Now the approach which is used for designing the interfacing circuit for any input and output device is primarily based on the instructions which are used for the transfer of the data. Now, any input and the output devices can be interfaced with 8085 microprocessor in two modes. One is the one way of interfacing is the peripheral input output, and second one is the memory mapped input output. In case of peripheral mapped input output, the instructions which are used are the in instruction for reading the data and out instructions for writing the data. But in case of memory mapped input output, all the memory related instructions which are used to transfer the data in between the processor and the memory, the same instructions will be used for the input output devices. One more important thing which is going to differentiate between peripheral mapped input output and memory mapped input output is, in case of peripheral mapped, we will be using 8-bit address to address the ports at which the peripheral devices are connected. But in case of memory mapped input output, we will be using 16-bit address for the individual peripheral devices. So we will be discussing both the methods of interfacing the input output devices, that is peripheral mapped input output as well as the memory mapped input output. Let us first discuss the peripheral mapped input output. Now in 8085, as I told you that in case of peripheral mapped input output, we use two instructions, in and out. In instruction to read the data from the input device, and out instruction to write the data into the output device. And both these operations, that is reading of the data as well as the writing of the data, is done with the reference of the microprocessor's accumulator. Meaning thereby, if we want to read the data will be read from the input device through the in instruction, and it will be stored in the accumulator. And whenever we want to write the data, the content of the accumulator is copied into the output device. So now both these instructions, that is in instruction and out instruction, has a certain format of use. Both these instructions are 2-byte instructions. 1 byte is meant for the in operation or the out operation, and the second byte is meant for the 8-bit port address. So you can say that both these instructions in and out are 2-byte instructions having their hexadecimal codes, and the second byte will be defined by the port address of the input device or the output device. One more thing which is important, since we are discussing peripheral mapped input output, so in that case we will be using 8-bit address for addressing the ports at which the peripheral devices are connected. So since we are using only 8 address lines, so 2 to the power 8, so it means 256 different addresses can be generated. It means we are restricted to use only 256 ports having their you can say having the different addresses which can be generated and given to the individual ports. Now, as far as these instructions executions are concerned, now since both the instructions in and out instructions are 2-byte instructions, but these two instructions, so minimum number of machine cycle which is used to take is 2. And these two machine cycles will be involved in such a way that in the first machine cycle, it will be fetching the opcode of the in instruction or the out instruction, and the second machine cycle will be fetching the address of the port. And in the third machine cycle, the address of the port will be placed on the address bus, and the control signals will be generated for enabling the port, and then the data is being transferred. So meaning thereby in and out instruction contains 3 machine cycles. It used to consume 3 machine cycles, and the total number of the T states will be 10, because opcode fetch will be 4, memory read will be 3, and then memory read or the write, it will be 3. So 4 plus 3 plus 3. So it will be taking full total, in totality, 10 T states and 3 machine cycles. In the first machine cycle M1, the opcode will be fetched, and how it will be done, the microprocessor will be placing the higher order memory address on the address bus, higher order bus, and the lower order memory address on the lower order bus. And at the same time, the ALE signal is as well as the input output memory signal is going to become low. ALE signal goes to high, and input output memory signal goes low. Why input output memory signal goes low? Because we have to work with the input output device. So these two control signals are conjuncted in a single signal. If it is high, it means it is an input output operation. If it is low, it means it is a memory related operation. An ALE signal just indicates the availability of the address, that is AD0 to AD7, and it can be used to demultiplex the bus. The input output memory, since it is being low, so that indicates that it is a memory related operation. But if it is high, it means it shows that it is a input output related operation. And in the third machine cycle, that is M3, what happens, that is either input output reading process or input output writing process will happen. And 8085, whatever address it has been read from the memory, it will be going to place that device address on the lower order address bus, as well as, and input output memory signal will be going high to indicate that it is a input output operation. So at T2, the accumulator content will be placed on the data bus, that is AD7 and AD0, followed by a control signal write if we are using a out instruction. If we are using in instruction, so whatever is the content of the input device, it will be placed on the data bus, and through the data bus, it will be coming to the accumulator, and at that same time, read signal will be going low. So this is how the in instruction and the out instruction used to work with the microprocessor. Now the device selection, as well as how the device is being selected and how the data transfer used to take place. Now, the objective of interfacing any device, which is either as a output device or the input device, is to get the information. If it is an input device, to take the information, or if it is an output device, to send out the result from the processor. So if it is a input operation, so device will be, microprocessor will be ready to read the content of the input device. And if it is an out instruction, the the data from the microprocessor will be sent to the output device. Now, if we talk about the out instruction, it is going to serve the purpose during the M3 cycle of the out instruction. The processor is going to place the information, that is accumulator content, on the data bus. Similarly, in case of in instruction, M3 cycle will be, in the M3 cycle, whatever is the content of the input device, it will be placed on the data bus. So if it is an instruction, the content which is placed on the data bus will be coming to the accumulator. If it is an out instruction, the content of the accumulator will be placed on the data bus, and through the data bus, it will be going to the output device. Now, the important point which I want to discuss here, suppose we are working with the output device and we are using an instruction that is out instruction. Now, and this output device is suppose the display, LED display, or it may be a printer. Now, the point here is that when should we enable the latch to catch that information? And second one is the what should be the address of that particular latch. So first question and the second question, when we should enable the latch, and when the and where, what should be the address to be latched. Now the answer of both this question can be arranged in the M3 machine cycle, and the latch will be enabled only when the input output memory signal is going to become high, as well as the write signal is going to become active low. Similarly, the address of an output port is also on the address bus during the third machine cycle, that is M3. And now the task is to generate one pulse, which will be used for the decoding the address, that is A7 to A0, to indicate the presence of the port address, in which we are interested, and generate a timing pulse by combining it with the input output memory and the write signal to indicate that the data byte we are looking is on the data bus, and use these pulses to enable the latch. Now these steps, you can summarize these steps in this way: that first of all, decode the address bus to generate the unique pulse corresponding to the device address on the bus, that is called the device address pulse or the input output pulse. Second one is the to combine or AND the device address pulse with the control signal to generate the device select, that is input output select pulse, that is generated when both the signals are asserted. And use this third one is the use this input output select pulse to activate the interfacing device. Now here you can see that we have a block diagram which is going to illustrate all these three steps for the interfacing of any input and the output device. Now in this particular figure, you can see that we have an address lines, that is A0 to A7, and these address lines are connected to the decoder, which will going to generate a unique pulse corresponding to the each address on the address lines. And this pulse, which is being generated by the decoder, it is later on combined with the control signal, which is generated signal with the this signal is combined with the control signal. Either if it is an input device, we will use IOR. If it is an output device, we will be using IOW. So this pulse is going to generate a device select pulse. Now this is the device or the input output address pulse which is generated by the decoder. Here we are going to combine this address pulse along with the control signal to and it is being ANDed together to generate a device select pulse. And this device select pulse is going to enable the output latch or the input buffer. Output latch or the input buffer. One more thing which is very important here: when we use latch or when we use buffer. Whenever a microprocessor has to send the data to the output port, we will be using latch. And whenever input device is going to send the information to it is being buffered. So you have not to be confused with that. We will be using this pulse which is generated just to enable the either the latch or the buffer, depending upon the device address and depending upon the ANDing of the device address and control signal to generate a device select pulse. So meaning thereby device is being selected with two control signal, two signals. One is address pulse and another is the control signal with which it is going to generate the device select pulse. Now, the illustrated diagram that how to decode the logic if we are using in an output port, and that output with that output port, suppose LED is being connected. This is going to show you the practical decoding circuit for the output device with an address with an address 0 and 1. Now, why it is 0 and 1? Because the rest of the, the address lines which are connected with the 8 address lines are connected with the NAND gate that functions as a decoder. Here we are not using decoder, but we are using the NAND gate which works as a decoder. Now, a line A0 is connected directly. If line A0 is connected directly, so it means it should be 1, and A1 to A7 is connected with the inverter to the NAND gate. So to generate a proper address pulse here, the A0 should be 1 and the rest of the value should be 0. Because if it is 1 and here all A1 to A7 is 0, here we will be getting 1 at each input. And once it is a NAND gate, all inputs are 1, so output will be 0. And when the output will be 0, then only it is going to generate the device select pulse. Now, this is gate G1, and we are using another gate that is G2. G2 is the AND gate, which is going to combine the address pulse with the control signal. Since we are connected the LED port, so LED is an output device. So it means microprocessor wants to write something. Now, for writing something, we have to generate input output write signal. Input output write signal can be generated whenever the write pulse is low and input output memory pulse is high. Because whenever it is low, it will be here, it will be 1. If it is high, it will be 1. So 1 and 1 is going to give the NAND gate output as 0, which is the device select, which is a control signal, that is IOW, because IOW can be asserted and will be active whenever this signal is low. So this has to be 0. So 0, so we are getting a value over here and value over here, and combining these two with the help of an AND gate, so we are able to generate device select pulse, or you can say it as a input output select pulse. This is called input output write signal. This is called input output address. So input output address is combined with the input output write signal to generate a pulse, and this pulse is known as input output select. And this input output select is going to enable the latch, because we are using output device, so we have to latch the data. Whenever we will be using the input device, instead of latch, here we will be using the buffer. So this is the control logic of decoding logic for the LED output port. So to do this operation, the G1 is going to generate a low pulse. Otherwise, the output remains high. And G2 is going to generate, G2 is combining the signal which is generated by G1 as well as the signal which is generated by IOW to generate the input output select. And when both the inputs are low, this and this, the input output select signal is going to be generated. And this happens in the machine cycle 3. Now, if this is so, the content of the accumulator, which is placed on the data bus, are now available on the data bus. And within a few microseconds, it is being latched, since latch is enabled. So within few microseconds, it is going to latch for the display on the LED screen, LED port, output port at which the LED is connected. Now we have, for addressing the different devices, peripheral devices, we have two types of decoding processes being used. One is called absolute decoding and another is called partial decoding. And in case of absolute decoding, all the address lines, suppose we are using 8 address lines, So all these 8 address lines are decoded to generate one unique output pulse. For example, this one. We are using all these 8 address lines to generate a unique input output pulse. This is called absolute decoding process. And it's a good practice to use the absolute decoding. But however, just to minimize the cost, the output port can be selected by decoding with only with the certain address lines. This is an example of the partial decoding. Because in partial decoding, it is not necessary that all these address lines will be used to decode the address of the output port or the input port. So here what is done, instead of A0 and A1, the write signal and input output memory signal are being connected besides A0 and A1. And A0 and A1 are not connected. They are replaced by input output memory and the write signal. And because the address lines A1 and A0 are put in the don't care condition. If we are using this kind of partial decoding, we are going to reduce our circuit. So we have not to use this particular NAND gate here to generate a pulse. And another thing is that we have not to use this one also. So what it will be simply doing, instead of, so it is going to, partial decoding process is going to reduce the hardware. That is why partial decoding is said to be more economical than the absolute decoding. But in every case, we cannot use the partial decoding, and that is why partial decoding process is used in a very small system. But normally we used to use the absolute decoding. So the difference between partial decoding and the absolute decoding is depending upon the requirement. If we are able to remove few of the address lines, and in place of that address lines, if we are able to connect the control signals along with the address lines together in a particular decoding circuit, that is called partial decoding. Now, how the input interfacing is being done, how we are doing the input. You have seen just now we are using output interfacing. Now we are going to discuss about the input interfacing. Now this figure is going to show you the interfacing of the 8 key input port. Here 8 keys are connected. So we are trying to connect a keyboard which is having 8 key, and it is through the input port. Now the basic concept behind this circuit are very much similar to the interfacing concept which we have discussed right now for the output device. Now same way, the address lines will be used for decoding by using a NAND gate. And when all these address lines are high, means A0 to A7 are high, that is, so it means if it all are high, it is going to give you the result FF. And the output of this NAND gate, will be going low if all these signals are high. If it is going low, and then it is combined with the read signal along with the input output memory signal. Since we have to work with the input output device, so this signal is high, read signal is low, because we want to read from the input device, that is keyboard. So it is going to generate an input output read signal, and this low address signal, that is input output address signal, and the low input output read signal is combined with the NAND gate, and it is going to generate a device select pulse. And whenever this device select pulse is going to be generated, it is going to enable this tri-state buffer. Now see the difference. Whenever we were using the output device to connect with the port, we were using latches. But in this case, since input device is connected with the port, so we have to enable that port with the tri-state buffer. So So whenever the microprocessor is going to execute the instruction, if instruction is written in FF, so the gate G2 will be able to generate, this G2 will be able to generate the device select pulse, which is used to enable this tri-state buffer, and data from the keyboard, data from the keyboard are put onto the data bus, and through the data bus, it will be going to the accumulator. Now, uh, how it is being done, we have to generate a control signal for the, since we have to do the reading process, so we have generated the control signal input output read. But in place of that, if it is a write, if there is a, device which is you can say that if it is an output device, then in that case we have to use the signal input output read. So two devices can be connected together as an input device and the output device. And in that particular case, now this kind of circuit in which we are using NAND gate for decoding, we can use only one output at a time. So if we have to connect with two different devices, one is input port, another is the output port, then in that particular case, this circuit cannot be used. In that particular case, we will be using a decoder circuit, which will have that it will have the 3 input and it will have the 8 output, and the individual output can be connected to the different ports, whether it is an input port or the output port. So the facility which we are getting with the decoder circuit is that more than one ports can be connected together. Now this is an example of how we are going to use the interfacing using the decoder, and in this case you can see both the devices, that is tri-state buffer is being used for the input, and the latch which is used for the output. And in this case, what is being done, this figure is going to illustrate the scheme of the address decoding. In this 3 to 8 decoder are used along with 4 input NAND gate is used to decode the address bus. The decoding of the address bus is the first step. Now, decoding of the address is the first step in interfacing the input output device. The address lines, which is A0 to A2, are used to input the decoder, and the remaining addresses, that is A3, A4, A5, A6, and A7, are used to enable the decoder, because A3, A4, A5, A6 is going to enable the enable 1, enable 2, and A7 is going to enable the 3. So the address A7 is given directly. So A7 should be already connected to E3, so it should be 1. So this decoder will be enabled if we get 0, 0 here, and E3 at E3, we should get 1. So now this decoder will have different outputs. 8 outputs are there. If we are considering it as O0, so O0 contains the value 0, 0, 0. A3 should be 1, 1, 1, 1, and A7 should be 1. So the result will be F8 will be the address. Similarly, if we are using O2, O2 means 0, 1, 1. So in that case, we will be getting, and A3, A4, A5, A6, and A7 will be 1. So the address which we generated is F8. Now, once we are able to generate the different addresses through this 3 to 8 decoder circuit, now the second step is to combine the decoded address with the appropriate control signals to generate the input output select pulse. Now this figure is showing you that output O0 is connected, O0 of the decoder is logically ANDed in the negative AND gate with the low input output right. So it means it is going to connect it with the output port, and the output gate, now the output of this particular gate is going to select the latch. It is going to be connected with the enable line of the output port. Once it is being done, the third step is to use this pulse to enable the output port. Now this figure is again showing that input output select pulse enables the LED switches, LED latches, with the output address F8H as shown by a combination of A0 to A7. And this is later on is being demultiplexed, and later on this data bus will be loaded by the content of the accumulator, and that through that data bus the address the content of the data bus will be arriving at the LED port. Similarly, O2 is connected with another negative AND gate along with the signal input output read, and this is going to generate the input output select for the input port with which tri-state buffer is connected. So once address is decoded, signals are generated, it is combined with the AND gate, NAND gate, and it is going to generate the input output select pulse, which is going to enable the tri-state buffer. So whatever is the content of these switches, it will be loaded onto the data bus, and through the data bus, it will be copied into the accumulator. So in this way, the interfacing of the input and the output devices are being done. Now, as far as the important concepts are, I'm going to revise the concept related with that. So whenever an input output instruction is executed, the microprocessor is going to place the device address since the device is connected with the port. So basically we call it as a port address on the demultiplex lower order address bus as well as the higher order address bus. Either the higher order or the demultiplex lower order address bus can be decoded to generate the pulse corresponding to the device address on the bus. Once the device address pulse is generated, it is ended with the appropriate control signal if it is a reading operation or it is a writing operation. And when both these signals are being asserted, the input output port is going to be selected. As interfacing devices, latch is used for the output port and the tri-state buffer is used for the input port. And the address bus can be decoded by using either an absolute or the linear select decoding technique. The linear select decoding technique is also known as the partial decoding. And the linear select decoding technique reduces the component, and so it is going to be economical, but the input output devices are ends up with the multiple addresses, because in this case if we are using instead of using absolute decoding, if we are using partial decoding for a particular input output device, we can get the multiple addresses. So partial decoding is used in the small system, but for the large system we always prefer to use the absolute decoding.